So when you conduct this autocorrelation plot of residuals in R, the first thing you need to do is calculate the length of the residual series, and then what you have to do to calculate the lag zero residuals, you actually lose one observation, actually the first observation, so this works slightly differently to how you might imagine it. Okay, and the easiest way to code this is call this thing here residual series, but from the observation numbers to, that's why you need to know the length. And then these lag one residuals, again this works slightly differently to how you might imagine it would. You again lose one observation, actually the last observation. Okay, so you need the square brackets here, the first all the way up to the 32nd observation in the residuals, and this is the into R. Once you've done this, you just need to use the basic plot command. Okay, now the reason this is actually informative is I think it's actually clearer once you follow this approach to see what's actually going on, and what you would expect to see with this plot is some degree of positive autocorrelation between the lag 1 and the lag 0 residuals. Okay, so it's actually clearer in some sense because you can see from the picture what's going on with these residuals. So works similarly in eView, so it's a little bit more fiddly. So what you would do is generate this thing here, resid L2 equals 0, and sample 1 to 32, because you're going to have one observation fewer compared to the original sample. And then what you would have to do is copy in all but the first observation from this original residual series. You would generate this here, generate resid L1 equals 0. Again, you'd need to enter sample 1 to 32. You can include one observation again. It's copying all but the last observation from the original residual series. And I think what you're beginning to see here is an example of something which is harder and more fiddly to do in eViews because it isn't as high a level programming language. It's not as easy to code as R is. And to lagged residual series, you would just do quick graph, and then you need the first series to be the lag 1 residuals, the second series to be the lag 0 residuals, collect scatter. It's similar to the R example, but the R example is actually easier in this case because it is all command line driven. Okay, whereas eViews, it's menu driven, but it's slightly fiddlier as soon as you get to something non-standard. So what you have here from this autocorrelation plot is that there is some suggestion of positive autocorrelation. So on the x-axis we've got the lag 1 residuals, on the y-axis we've got the lag 0 residuals, and if you sort of squint a bit you can imagine drawing a sort of straight line roughly halfway through this cloud of points. Okay, it's not perfect, it's not the sort of perfect correlation that we've got in some of the early graphs in the first couple of lectures, but you can see there's clearly a positive autocorrelation here, and this makes sense because what this is saying is that if you've got large residuals at one moment in time, the next residual is also likely to be large as well. Okay, and this makes sense in the wider context because our data set is a set of market prices here, inflation adjusted gold and inflation adjusted stock market prices, and we naturally would expect autocorrelation to occur in this instance precisely because we're collecting market data over time. Okay, and I think this autocorrelation plot is giving you some information here and is giving you a feel for what's going on. It's natural to expect some positive autocorrelation here. Again, this reflects that if the residual is large for say the year 2000, then you're more likely to also get a large residual for the next year, year 2001. I wanted here to talk about statistical tests for autocorrelation. So there's three main options and we'll go through the first two options. The third one is mainly just of theoretical interest. So the first example is a runs test. So the idea is that if the classical multiple linear regression model is correctly specified, then the residuals are equally likely to be positive or negative. So we've seen an example of this one of the graphs that sometimes if the regression model isn't correctly specified, then you get what are called runs of residuals that either take all positive values or negative values, and this wouldn't happen if the regression model was correctly specified. A second example test that we're going to look over is this classical Durbin-Watson test, and the idea here is to test if the residuals are autocorrelated of order 1, and this would reflect the graph that we showed you previously, that you often get correlation between successive residuals. Okay, so in our lecture example, you might have consecutively large residuals for the year 2000 and the year 2001, and then there's this extra Buisch-Godfrey-Lagrange multiplier test, which gives you a more general test for autocorrelation, but is really outside the scope of this introductory course. So the runs test is conceptually simple, not very powerful, and again the basic idea here is that if the regression model is correctly specified, then it's a 50-50 coin toss whether or not the residuals are positive or negative. Now what can often happen is if the regression model is not correctly specified and there's some autocorrelation present, then you tend to get runs of residuals that all have the same sign. So what you have here is that R is the number of runs, the expected value from here, it's given by the third equation. What we've got here is that n equals the total number of observations, and 1 is the number of residuals, and you would perform a t-test using the bottom of your t-tables, which is just an approximation based on the normal distribution. So it's the same basic format. So you would have in this case r minus the expected number of r divided by standard deviation. And the idea would be that you would compare these to tables, or you would be able to extract the p-value using R. Okay, and this is certainly what we will discuss here: how to both do the hand calculation and how to extract the p-value from R. So in this gold market example, so the residuals have these following signs, and so what you should see in here is you get these clustering of negative residuals, then a cluster of positive ones, negative and positive, a larger string of negative and a string of 3 positive residuals at the end. So there's some indication there that you get clumps of residuals of the same sign, so possibly some autocorrelation. This, it turns out, gives us 6 runs of residuals which each share the same consecutive sign. So we have here 10 positive residuals, 23. So you can form the statistic in this case like this, and it turns out that the statistic is 3.765. The value needed from tables is 1.96. So the t-value is bigger than 1.96, which is the right value from tables. So using the little trick that if you're doing this correctly, the inequality signs put in a different way, this indicates that p is less than 0.05. So there is evidence from the runs test that there is autocorrelation in the residuals. And this is something that is relatively straightforward to perform in R, as we'll show you in the next slide. So how you do this in R is that first of all you need to produce a character vector that determines if the residuals are positive or negative using the command factor. So what the command factor does is just give you what's called a character vector, which would in this case tell you whether or not this condition here is true or false. So this would be true if the residuals are positive, false if the residuals are negative. And then you would need to code this, it's called T-series in R. So these things are deliberately named, and as you might imagine, T-series is short for time series, and then you would need to apply the function runs.test to this here. you need to do runs.test of this resid sign variable here. In this case, what you find is that the minus 3.7653 value is 0.00163 less than 5. So this presents evidence that the residuals are autocorrelated. Okay, so this essentially just reconstructs the previous workings that we've done by hand on the previous slide. So this leads me to a discussion of the optional packages that are available in R, and really the best thing about R is this large online community that write packages and code for it, so you don't have to write your own coding for quite a lot of the standard things that you would wish to do. So if you want to run a runs test in R, to do this you have to download the R package T series, which, as the name suggests, does stand for time series. So in R, to upload packages, what you need to do is packages, load packages, T series, and click OK, and then just follow the commands on the screen. So it can be a little bit fiddly the first time you do this, and then I think once you've done the loading the packages once in R, it should be relatively straightforward. But do speak to me in person about this if you want to go through how to download these optional R packages. Okay, and I suspect this is one of the things that will actually work better on your own laptop compared to working on campus, even if you had full access to campus. Okay, and then just to reinforce then that really this is one of the best things about R. There's a large online community that provide these optional packages, so there's an awful lot of code that's freely available on the web. It can save you a hell of a lot of work potentially. So I just wanted to say a bit more then about how to install non-standard R packages from CRAN. CRAN, remember, just stands for the Comprehensive R Archive Network. So in R, to see what packages are available for downloading, use packages, load packages. If the package is not there, you might have to download the required package from CRAN. So to do this, you just need to do packages, install packages, and then use a CRAN mirror. And then if you're based in the UK, it is better to choose one of the UK options, London or Bristol. Can't remember which one works better. Possibly Bristol, but I wouldn't swear to it. Just have to experiment with one of these here, and then once you choose one of these options, either London or Bristol, you should see a long list of packages that are available for download. Okay, there's a hell of a lot there, and again, the best thing about R is this huge online community that provide these packages. Okay, and there's almost any kind of statistics that you could wish to imagine that has a R package attached to it. And again, if there was any doubt, this online community and long list of written packages that you can download for free is really the best thing about R. And again, if you've got this online community, you can almost just teach yourself by looking on the internet, seeing just how much code and hints, etc., are available for free. Now, when I've worked at universities in the past, they've had problems with the computer network as far as R is concerned. Now, as far as I can see, this shouldn't be a problem with the University of Bradford, but has been a problem with other universities that I have worked at. So on my work computer, standard packages actually loaded fine. One university I worked at, this wasn't the case. On your personal computer, you should be able to update the list of packages via the R repository CRAN, so certain things might actually work better on your personal laptop compared to a campus PC. It may not be possible to update packages directly on a PC on the university network, so this was a problem, like I say, at one of my previous institutions, but it wasn't a problem last year that I had at Bradford. Now, if you do have this problem, the campus PCs, the workaround around this is to save the package code to a USB stick and then do packages, install packages from local files, and then you can install a package from the USB stick. Okay, so there is a workaround on this, but I don't think this should be a problem at Bradford. best thing, as with all these things, is bring your laptop to class and we see if we can get the thing working. It's not always easy. It should get easier the more you practice. On my laptop, I found loading R packages fine, but fiddledier than it should have been. But once I got it working once, it was much easier after that.